Now we move ahead to learn the scalar product, or also called as dot product, of two vectors. Now it's like in algebra we do the product of two numbers. So similarly in the vector world we are doing a product of two vectors, but of course it is different than the product of two numbers. So the scalar product is denoted as a bar dot b bar as shown here, and it is defined as mod of a bar, that is magnitude of a bar, into magnitude of b bar into cos theta, where theta is the angle between vectors a bar and b bar. So that's the definition of scalar product. Now if we look at the right side, we know that the magnitudes are nothing but the scalars, they are pure numbers, and cos of any angle is also pure number. So it means the right hand side as a whole is a pure number, it's a scalar, and that is why we call this as a scalar product. Okay, so although there are two vectors on left side, their scalar product gives us a scalar, that is a number. Okay. Now to get the scalar product, let us first derive the scalar products of the fundamental unit vectors. That is, let us first consider what will be I cap dot I cap. As per the formula, it is magnitude of I cap into magnitude of I cap into cos of what is the angle between I cap and I cap itself. Now if it is the same vector, then obviously both have the angle of 0 between them, isn't it? So that further equals magnitude of I cap is 1, because I cap is a unit vector. So 1 into cos of 0 is once again 1. So therefore finally the answer will be 1. So that means if we have the dot product of two identical unit vectors, that will always be equal to 1. So similarly we can show that j cap dot j cap is 1, as well as k cap dot k cap is also 1. Now let's see what happens when we have two dissimilar fundamental unit vectors. So in case of I cap dot j cap, we have the first two magnitudes into cos of, now just recollect what is I, j, k. Here you have I, here you have j, and here you have k. You see the angle between I and j is 90 degrees. So that is where we will have cos of 90 degrees. And we know that cos of 90 degrees is 0. So therefore straight away we get this dot product as 0. So similarly we can show that j cap dot k cap is also 0, because between j and k also we have 90 degrees. And k cap dot I cap is also 0, because they also have 90 degrees angle between them. Right? So we make use of these facts to actually calculate the scalar product. So that is what we have, the working procedure to calculate the scalar product. So that means if we are given two vectors, say a bar and b bar, with their individual I, j, k components as a1, b1, c1 and a2, b2, c2, and we want to get the dot product or the scalar product of a bar and b bar, then how to do that? Now if you observe, while doing the dot product, what we will be essentially doing is a bar dot b bar is equal to a1i plus b1j plus c1k dot a2i plus b2j plus c2k. Now while opening this, we would be multiplying the first term with the first term, then first term with the second term, first term with the third term, right? After doing this, we will take up the second term and multiply it with all the terms in the second bracket, right? And finally we will take up the third term and multiply it with the three terms in the second bracket. Now you see that whenever we are doing the dot product of two terms involving the same unit vector, that is I, jj or kk, that product will be a non-zero number, that will be defined, like assuming the magnitudes of I, j and k are non-zero. But whenever we are doing the dot product involving two different unit vectors, that is I and j, we have already seen that I dot j turns out to be 0. So therefore those products will be 0. So that means what we have to do essentially is we have to consider the dot products of the like vectors, that is I, j and k, and hence a1 I cap dot a2 I cap will be nothing but a1 into a2 because I cap dot I cap is 1. Similarly, we will have the second product as b1 b2 and third product as c1 c2. So that is how we use the working procedure. That is, this is the actual procedure when we are to calculate the scalar product. So we multiply the corresponding coefficients of I, j and k. Let us go ahead and see some of the important properties or deductions based on the definition of scalar product. Firstly, we have a bar dot b bar equal to b bar dot a bar. Again, this is called as the commutative law. That means even if you change the order of vectors in scalar product, the final answer remains the same. Second is a bar dot b bar plus c bar is equal to a bar dot b bar plus a bar dot c bar. So it is very much equivalent to opening of the bracket that we use in algebra. This is called as the distributive law. It's the distribution of scalar product over addition of vectors. Now third one is again a very useful result, that is if a bar is perpendicular to v bar, then their scalar product is 0. Simply because if two vectors are perpendicular, then angle between them would be 90 degrees, and hence since cos of 90 is 0, their scalar product turns out to be 0. This is a very important property that we use in many sums. Then next property is a bar dot a bar is equal to magnitude of a the whole square. Once again, this comes from mere writing of the expansion, that is a bar dot a bar is mod a into cos of 0, because the angle between the same vector a bar and a bar is of course 0, which gives us 1, and hence ultimately we have the square of the magnitude. And lastly, we have cos theta is equal to a bar dot b bar divided by mod a into mod b. And this also comes from the original definition of dot product, because a bar dot b bar was nothing but the product of mod a into mod b into cos theta. So if we know the two vectors, then we can also find out the angle between them, and we can find out their dot product. Let us solve one example based on the scalar product. If a bar and b bar are given as shown here, then find a bar dot b bar and also the angle between a bar and b bar. So let us first find out their dot product. Okay, here what do we do is we multiply the corresponding coefficients, which is 3 into -1. Then in case of j it is 1 into 2, so that is plus 1 into 2, and in case of k it is -4 and plus 1, so it is -4 into 1. So that gives us -3 plus 2 minus 4, which is nothing but -5. Now to get the angle between the two vectors, the formula is a bar dot b bar upon mod a into mod b. We have already got a bar dot b bar as -5. We have to now calculate a bar and b bar magnitudes. So let us calculate them and then put it in the formula. Magnitude of a bar will be given as square root of 3 square plus 1 square plus -4 the whole square, which is equal to 9 plus 1 plus 16, which turns out to be root of 26. Let us calculate b bar now. Mod of b bar. So that is equal to -1 the whole square plus 2 square plus 1 square, which further is equal to root of 1 plus 4 plus 1, which is equal to root 6. So therefore cos theta is equal to a bar dot b bar is -5 divided by root of 26 into root 6. So that is equal to minus 5 divided by root of 156. If we want to find the acute angle, then we have to take the modulus, because cos of an acute angle will be positive. So in that case we will skip the negative sign and cos of theta will be 5 upon root of 156, and the actual angle theta will be the cos inverse of this particular number. Okay, so we need not find what is that exact angle. It is sufficient to write theta is equal to cos inverse. So cos inverse means it is that angle whose cos is this particular specified number. So that's the way to calculate the scalar product as well as the angle between any two vectors given.